Today we're going to continue inequalities. Today all of the rules are the same, but we're going to be working on compound inequalities, which means that they're two-sided. They're essentially two arrows. They're two inequalities. There are two basic types. We have an OR inequality, which would look something like this, say 5 and 7, and you have an arrow going one way and an arrow going the other way. And basically it says, in order to be a solution to this set, you have to satisfy one of the arrows or the other arrow. One or the other. That's why it's called an OR. You obviously can't be in both at the same time. There's no number that is smaller than 4 and bigger than 7. You're either smaller than 4 or bigger than 7. The other type is called an AND. An AND would look like this. We could have a 4 and a 7, and it would be everything in between. So essentially, this is an arrow that way, and we have an arrow that way. And you satisfy one of them and the other one. An OR means you satisfy one or the other, and means you have to satisfy both. So, is 5 a solution to this set? 5 is bigger than 4, and it's smaller than 7. What about 10? 10 is bigger than 4, but it's not smaller than 7. I don't think this happens today, but theoretically, you could have one that looks like this. X is bigger than 4, or X is less than 10. And if you were to graph that, so here's 4, and here's 10. Bigger than 4 would be over there, and less than 10 would be over here. What number satisfies one or the other? And the answer is everything. Every number is either bigger than 4 or smaller than 10. So if you have an OR that faces towards each other, the answer is the entire x-axis, because everything satisfies one or the other. But I don't think that happens today. In general, OR has a gap in the middle, and AND goes toward the middle. So essentially, an OR statement is simply two inequalities. For example, I could have 2x plus 4 less than or equal to 10, and 3x greater than, greater than or equal to, let's say, 15. And then it will say OR in between. So either 2x plus 4 is less than or equal to 10, or 3x is greater than or equal to 15. You just solve each one separately. So I would subtract 4, 2x less than or equal to 6, divide by 2, x is less than or equal to 3, or divide by 3, x is greater than or equal to 5. To graph that, I would put a mark at 3, filled in, less than would be to the left, a mark at 5, filled in, greater than would be to the right. So an OR statement goes in both directions. You just solve each one separately and graph them separately, and the answer is one side or the other. There are two different ways to represent an AND. One is just sort of like the OR. Let's say I had 3x less than or equal to 18 and 2x minus 2 greater than or equal to, let's say, 4. And there's an AND between them. So in order to be an answer, you have to satisfy the first one and the second one at the same time. Solve each one. X is less than or equal to 6, and if we add 2x greater than or equal to 6, we divide by 2, x is greater than or equal to 3. In this case, I have a 3 and a 6. And it would be everything bigger than 3, so to the right, and everything less than 6, which would be in the middle. But because this is an AND statement, I don't go forever in both directions. It has to satisfy both, which means the answer is between 3 and 6. So in order to be part of the solution set, you have to be bigger than 3 and less than 6. Now, you'll see some of these on the worksheet, but once you get good with this and you go a little bit higher in mathematics, you stop seeing AND statements in this form. They always look like this. 10 less than 2x plus 8 less than or equal to 24. This is an AND statement. That stuff in the middle is bigger than 10 and it's less than or equal to 24. So this is another way to represent an AND statement of a compound inequality. The tricky thing is, we're used to saying whatever you do on one side, you do to the other. But in this case, the inequality has 3 sides. There's an original inequality, a middle, and then one at the end. Solving is pretty much the same. You subtract 8, but you have to subtract 8 from all 3 sides. So subtract 8 there and subtract 8 there. 2 less than 2x, which is less than or equal to 16. Does everybody get that? And then divide by 2, but you divide everything by 2. 1 less than x less than or equal to 8. And this setup is really nice. X is sandwiched between 1 and 8. If you start from the middle, you'll see x is bigger than 1 and x is less than or equal to 8. On the number line, you have 1 with an open circle and 8 with a closed circle, and it's everything in between. Okay? Now, you cannot represent an OR statement like this. If you do 2 inequalities in the same sentence, it has to be an AND statement. If you tried to set up an OR statement as a compound inequality, for instance, you had 6 is greater than x, which is less than or equal to 8. So if you went from 6 this way and 8 that way, you look at the answer there and it can't work. Can x be smaller than 6? Oh, did I do it wrong? Can x be smaller than 6? And I get this backwards. Greater than 8. Can x be smaller than 6 but be bigger than 8? No. So OR statements have to be written as 2 inequalities. AND statements can always be written as a single inequality. All right. One more I want to do, and then you guys can work on your assignment. What if I had 4 less than or equal to 8 minus 4x less than, we'll say 20. What should I move first? The 8. I'll subtract 8 from all 3 sides. Negative 4 less than or equal to negative 4x less than 12. Divide by negative 4, and what is that going to do? It will switch both inequalities. 1 greater than or equal to x, which is greater than negative 3, and it still works. Can x be smaller than 1 and bigger than negative 3? Yeah, it just is turned around from the way you're used to seeing it. If you graph it, it still works. Negative 3 is over here with an open circle. 1 would be here with a closed circle, and x is bigger than negative 3 and smaller than 1. That would be the AND statement answer. All right? Good luck.